Dear engineers, welcome to VEDA Gate Academy and welcome to the world of opportunities. The topic here for sequential digital circuits today is assembling memory ICs. Assembling memory ICs to the higher size requirement. Taking two small size of memory ICs, assembling them and then molding to the next requirement. Here, before I speak about assembling memory ICs or assembling decoders or assembling multiplexers, assembling any two circuits to get a higher size, why do we need to assemble the smaller ICs to the bigger size? Why don't I directly use a bigger size IC? And that question raises what is your answer? Yes, please. Why do assembling plays a key role than the designing varieties of ICs? Yes, please. An example, if I know my requirement and predefined, may I directly design to my requirement. But when I'm using in real time, I do not know what size of ICs I would be required. Instantly it may be changing. Based on the application, at the particular incident it may be changing. So I must be prepared to assemble the available and use it, number one. My time in the remote area working, I don't have the direct size, a bigger size ICs available with me. And I have only a lower size ICs with me. Being a designer of electronics and communication, I must be knowing how to assemble them and use it. So, to meet instant requirement at working in remote areas, and not only that, I may not be able to design varieties of ICs by not knowing my requirement, just dump in the go down and or dump in the shop to use on. I would not be knowing how many will be sold or how many will be utilized or all. Rather, if I design standard size ICs, and then whoever want the higher size, they would be assembling the smaller ICs together and using. And designing only one few varieties of standard size ICs, manufacturing cost also will be reduced, where user also will get the ICs for the cheaper cost. And this is the inner logic behind assembling play a key role in the design of memories or multiplexers or decoders or any circuit, I can say. So assembling plays a key role than the design. Designing only a few standard size of ICs would reduce the manufacturing cost of the system, where I am benefited as a user to buy the IC with a lower cost. And then if my requirement is not directly available in the market, I would buy the suitable lower ICs and then lower sized ICs and assemble them and use it. That's a basic theme of assembly. Now let us see how do we assemble memory ICs. And we already learned how to assemble decoders. I already taught you 3:8 by 2:4, 4:16 by 3:8, 4:16 by 2:4. Similarly, in the case of multiplexers, we learned 4:1 by 2:1 and 8:1 by 2:1. All these kinds we have seen. Now, in the same way, let us see how the memory ICs are assembled. Yeah. Before we go to memory IC assembling, we have to go with address calculation. How do we calculate the address for memory IC? Every memory IC will have a certain address range, say 1K, 2K, 3, 4K, 8K, 256 bytes, 512 bytes, like that. Every IC will have a defined size. Let us see. Let us learn how to calculate that address. Address calculation. Sorry. Yes, please. 00 to FF, hexadecimal. How many lines, students? 00 to FF is of 256 lines, agreed? This number is 256. Continuation. 100 to 1FF, 200 to 2FF, 300 to 3FF. Are you clear? So, what are all this? Hexadecimal notations, right? So yes, please. 1002 1FF, again 256 lines. And this is again another 256 lines. Another 256 lines. Would you agree? Yes, you will. So how many pages? So 4 pages, right? Yeah. So 4 into 256 is how much? 4 into 256. Is it not 1024? Yes, it is. Is it not 2 power 10? So is it not 1K? Yes. If I assume that 256 lines is 1 page, so that means 4 pages. That means 4 pages of 256 lines is equal to 1K. So 4 pages of 256 lines is equal to 1K. Similarly, another 4 pages of 256 lines, 2K, right? Another 1K. So continuation. 400 to 4FF, 5FF, 6FF, 7FF, 4, 5, 6, 7, another 4 pages. So 400 to 7FF. So 400 to 4FF, 5 to 5FF, 6 to 6FF, 7 to 7FFF. So how many pages? Again 1K, right? This is another 1K. Notations. 800, starting from 800. 800 to 8FF, 900 to 9FF, 8, 9 after 10, but 10 is equal to A. So A00 to AFF, B00 to BFF. So it is then 800 to BFF. Another 4 pages. So 8 to 8F, 9 to 9F, A to AF, B to BF. So it is another 1K. Like that. Go with it. So C00 to C to CF, D to DF, E to EF, F to FF. C, D, E, F, another 4 pages. C, D, E, F, another 4 pages. So C00 to CFF. How many pages? Another 1K. Now, I just want a representation like this. Yes, please. Starting from 0000 hexadecimal. 0000 hexadecimal. So I want notations of 1K, 2K, 3K, 4K. Representation, please. So 1K, 4 zeros to 3FF, 0, 0, 0, 0 to 0, 3FF. 3FF is 1K, right? Yeah, 4 pages. Continuation. 0, 4, 0, 0 to 4FF. 7FF, I'm sorry. 7FF. Another 1K. I'm sorry, you have to write 2K, right? Sorry. Total 2K. Again, starting from 0, 0, 0, 0. 0, 0, 0, 0. So I have to go with 8 pages. So another 1K. So till 7FF. 0, 7FF is 2K. So starting from 0, 0, 0, 0. So he want a 3K. So BFF. 0 BFF. And starting from 0 C00 to 0 FFF. I'm sorry, C0 to CFF, 0 CFF. C to CF, D to DF, E to EF, F to FF. Sorry, here small correction. This is triple F. Correct. So 0C is 0 to C to CF, D to DF, E to EF, F to FF. So 0 triple F. Right? And this is how the representation of memory IC size will come into the picture. I hope you're clear now how to represent 1K, how to represent 2K, how to represent 3K, how to represent 4K, like that. So 00002 here, I'm sorry, 00002 everywhere starting from 000, right? 0 triple F is 4K. So like that, I can define 5K, 6K, 8K, 10K, any amount of size I am comfortable to. Just referring this concept. So if I just assume that 00 to FF for 256 lines is 1 page. So 4 of 256 lines, 4 pages is 1K, 8 pages 2K, 12 pages 3K, 16 pages 4K. And that concept I can follow to define the memory IC addressing range. And this play a vital key role, vital and key role to remember calculating the address from default of 0000. Now let us see how to calculate from a certain number. If it is from 0000, well fine, but if I want a address range from a given number, certain number, let's see how to do that. Example 1. $1K from 3C E9 hexadecimal. So I want to calculate 1K from 3C E9 hexadecimal. Here. (3C)E9, and this is already one line, plus 03FF, that is 1K, right? 0000 to 03FF, 1K, right? So adding 03FF, actually 03FF is 1023 only, including 0000 it is 1024. So 1 plus 1023, how much it is? 1024. I want 1K now. So here just make a note, important. The 03FF is 1023 only in decimal. Including 0000 it is 1024, 1K. So if I remove that, 03FF itself is only 1023. So one number 3C9 plus 1023 is definitely equal to 1024. Try to understand the logic. 1023 plus one address. So it is 1024. Make an addition. 9 plus F, 24. 24 is 16 plus 8, 1, 8. So 16 plus 14, 30. 30 is 16 plus 14. So 1, 14 is E. So C plus 3 plus 1. C plus 4, 16. 16 is 1, 0. So 3 plus 1, 4. 4, 0, E8. So it is that 3C E9 to 40 E8 is 1K. Nothing but 1024. Are you clear with the calculation? Now, I have an example too. That is $1K from, let me say, 1K from (4B76) hexadecimal. Let's better take 2K. 1K already we calculated, no? (2K from 4B76). Yes, please. Let's start calculating. So 4B76 is one line plus 2K is 07FF, right? Yeah. So 07FF is 07FF is 2047 2K. Decimal 2047. Including 0000, it will be 2048. Are you clear? Yeah, yes. So add 6 plus F. So 15 plus 6, 21. 21 is 16 plus 5. So 1, 5. 16 plus 7, 23. 23 is 16 plus 7 only. So 1, 7. So 8 plus B. B is 11. 11 plus 8, 19. 19 is 16 plus 3. 1, 3. So 4 plus 1, 5, 3. So 5375 hexadecimal. So what is the range? So 4B76 to 5375 comes as 2K. I hope you are clear with the calculation. Yes, please. Another small examples I have. Example 3. $3K from, say, 3973 hexadecimal. Sorry. So make an addition. 3973 hexadecimal plus 0BFF. So 0BFF is 3K minus 1. So 3K minus 1 plus 1, 3K. So make an addition. So 3 plus F, 14. 14 is E. Sorry, 3 plus F is 18. 18 is 16 plus 2. 16 plus 7, 23. So 16 plus 7, 1, 7. So 11 plus 1, 12 plus 9, 21. 21 is 16 plus 5. 3 plus 1 is 4. So 4572 hexadecimal. So it is 3973 to 4572 is of 3K range. Now I have another example, which is 512 lines from ACB2 hexadecimal. It's only 512 lines. Yes, please. 512 lines in the sense, I can say 2 power 8 is 256. So then 2 power 9. So 9 ones, right? So 9 ones, 1, 1, 1, 1. So 1, 1, 1, 1, 1, 1, 1, 1, 1. So 0, 0, 0. So it is 1FF 512. Yeah, 0 to 0F, 1 to 1F. Correct. So 1FF, if I add, it is 512 lines. Come back to ACB3, ACB2, hexadecimal, plus, so 0, 1FF. 0, 1FF is 511 decimal. So if I go to the next line, it is 512. 2 power 8 is 0 to 0F, 1 to 1F, 2 to 2F, 3 to 3F, like how we end. No? So 1FF is, 511. If you add all together, it is 511. So 512, right? So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. The next line is 512. So if I add all together, it is 511. Yeah. Addition, please. 2 plus 5. 2 plus F, sorry. 15 plus 2, 17. 17 is 16 plus 1, 1, 1. So 16 plus 11, 27. 27 is again 16 plus 11 only, 1B. So 2 plus C, 14, E. A remains the same. So AE B1. Acceleration. So it is that. AC B2 to AE B1. Sorry. AE B1 is 512 lines. I hope you are clear now completely how to calculate the address range for the memory ICs. Now, the very immediate topic is memory chip enable logic. How to enable memory ICs. Here, memory chip enable logic. Here, please. Assume that this is my memory IC. I have notations. Say 1K into 8. 1K means 10 address lines. So A0 to A9 address lines. 2 chip enables. Chip enable 1, chip enable 2 bar. So high enable, low enable. So into 8, no? So data D0 to D7. So 10 address lines. Here please. IC with 10 address lines, 8 data lines, comma, 2 chip enable lines. 2 chip enables. Now based on the chip enables, how the IC activation is? CS1, CS2 bar, memory IC. See this logic I have already taught you. In decoders I taught you, and even in memory ICs also, sorry, in multiplexers also I taught you. Nothing new, and this is known to you, just to revise once. If I get CS1 as 1, so high enable is high. High enable is high. This is not known. So low enable is low. This is not known. So in the first case, out of 2 enable signals, 1 is known, the known is on. I have already told you this condition, and this is called as partially on. So if 2 chip select signals are there, out of which 1 is known, the known is on, it is partially on. 1 is known, the known is on, it is partially on. Second case, if I get 0 on CS1, I don't bother about second. 1 on CS2 bar, I don't bother about second. So this condition, ICs are completely off. Because 1 is known, the known is off. High enable given with low. Low enable given with high. Ultimately it is off. The one and only case to enable this chip IC is 1 on CS1, 0 on CS2 at the same time. Then only IC is on. When we enable both the enable signals at the same time, then only IC is on. So I hope you are very clear about address calculation. 1K, 2K, 3K, 256, 512 of any number given to from a certain number or from a 0000. And also you are clear about how does this memory IC gets enabled based on CS1, CS2 bar status. Good. Now let's start working on the a topic of exercises, assembling really problems. Yeah. Here, design 2K into 8 ROM by 1K into 8 ROMs, 4K into 8 RAM by 2K into 8 RAMs for a digital system with the condition memory ICs with only one chip enables CS1, sorry, two chip enables CS1, CS2 bar. Look into that. So memory ICs are with only one chip enables CS1, two chip enables CS1, comma CS2 bar. Then design this circuit. Repeat once again. 2K into 8 ROM by 1K into 8 ROMs, 4K into 8 RAM by 2K into 8 RAMs. Now that means lower size ICs are available, and I want to make the larger size capacity of memory. So if I take 2 of 2Ks, sorry 1K, it will become 2K. 2 of 1K, it will become 2K. Similarly, if I take 2 of 2K, it will become 4K. So totally 6K memory I require. I should take 2 of 1Ks, 2 of 2Ks, 4 ICs together, assemble them, and I would be getting my requirement. True? Yes. Now let's see, how do we do this one by one. Step number 1, so you have to understand the problem first. So basic requirements. Yes, please. Step 1. Basic requirements. Basic requirements. Yes, please. Let's start from number of 1K into 8 ROMs required for 2K into 8. So number of 1K into 8 ROMs required for 2K into 8. Ultimately 2, right? Immediate. Number of 2K into 8 RAMs required for 4K into 8. Again 2, right? Now, third statement. Total number of memory ICs required. Aren't they 4? 2 plus 2. 4 ICs. Next. Number of address lines for 1K into 8 ROM. Similarly, number of address lines for 2K into 8 RAM. See, my requirement may be 2K into 8 ROM, but my availability is only 1K into 8. So I should just frame the address lines for available only. Number of address lines for 2K into 8 ROMs. So I should take 2K into 8 and make 4K into 8. I should take 1K into 8 and take 2K into 8. So hence, the address lines are, so 1K is 2 power 10, right? So 10 lines. 2K is 2 power 12 lines, right? That means 2 power 2 into 2 power 10. Sorry. 2k is 2 power 1 into 2 power 10. Sorry. So 11 lines. Notations, please. 10 lines are from A0 to A9. Correct? 11 lines are from A0 to A10. Till here, are you clear? 2 1Ks for 2K, 2 2Ks for 4K, totally 4 memory ICs, address lines for 1K 10, address lines for 2K 11. So out of which 0 to 9 are the common lines given. Next, immediate step. From this side. Yeah. Number of address lines common to ROMs and RAMs. And number of address lines to be used for chip selection, or I can say memory enabling. Yeah. Yes, please. So, number of address lines common for ROMs and RAMs 10. A0 to A9. And one more line extra, however required for this one. I have to write that, in fact. I did not write. Yeah. Extra address line for RAMs. So, one line. That is what A10th line. So, number of address lines to be used for chip selection. Here, to select 1 out of 4. To select 1 out of 4. Who are 4? 4 memory ICs are involved total. 2 of 1K, 2 of 2K. So, to select 1 out of 4 are ultimately 2, right? 0, 2. 2 lines. So, which are they 2? Already A0 to A9 for ROMs and A1, A10 for RAMs. So, remaining. So, those 2 lines are A12, comma A13. A12, comma A13 will be used for chip enabling. Now, tell me in the structure. So, A0 to A9 for ROMs identification and then A0 to A10 for RAMs identification. So, then after 10th tak we used, no? 11, comma 12, I'm sorry. Zero to 9, 10th is used. So, 11, comma 12. A11, A12 are used for chip enabling, memory IC identification. So, I have 4 ICs available. Only one must be able to work at a time. One should be able to work at a time. So, that is how I am using extra 11, comma 12. I hope the basic structure, step number 1, the requirements are framed. Let's see step number 2. Yeah. Step 2. Yeah. And the configuration of step 2, the process is hexadecimal address map. Yes, please. Hexadecimal address map. Let me do that. IC1, IC2, IC3, IC4. Right? So 4 ICs I have. What are the size of them? 1K ROM, another 1K ROM, 2K RAM, another 2K RAM. Now, he did not mention any space in address range. So, default takes from 0000. So, starting address not mentioned. Hence, start from 0000. Default. Default starting address is that only, right? Yes, please. 0000 from there 1K. So 03FF. Next. 0400 continuation, another 1K. 07FF. 0800 continuation, now 2K. 2K means 8 pages. 2K means 8 pages. So 0800, 8 to 8F, 9 to 9F, A to AF, B to BF, C to CF, D to DF, E to F, EF, F to FF. 8, 9, A, B, C, D. I repeat 8 pages, 8, 9, A, B, C, D, E, F, 8 pages. So the last one is 0FFF. 2K. Continuation. 1,000,000. 2, 8 pages again. 2K means 8 pages. So 1, 2. So 1F, 2, 3, 4, 5, 6, 7. So it is 17FF. The range for the required memory ICs is this. But we have to convert this into binary space map. Binary. Then only we'll be able to identify, right? So a hexadecimal address cannot be connected. We need low and high voltages. Voltage level map. So binary map I need. So my step 3 here is voltage level. Nothing but binary level. Space map. Space in the sense address space. Right. Now come back to speak. A0 to A15, A15, A14, A13, A12. Consequent 11, 10, 9, 8. Next we have 0, 1, 2, 3, 4, 5, 6, 7. So A4 to A7. A0 to A3. Hexadecimal map. Yeah, yes please. Now here I have IC number. IC1. 1K into 8, right? IC2, IC3, IC4. Yeah, IC1, 2, 3, 4 are framed to convert this into hexadecimal, binary space map. Yes, please. Since I am doing in hexadecimal, make it into 4-bit equivalent. 4-bit segregation. Yes, please. IC 1234 4-bit segregation. Who are the address lines? For ROM 0 to 9. For RAM 0 to 10. Is that correct? Yes, please. So, address range for ROM 0 to 9, 1K. Address range for RAM 0 to 10, 2K. And who are the chip enable lines? 11, 12. These two. Who are they? Chip select lines. Chip select lines. Now let us see how do we define the address. Yeah. Address lines of all. IC1, ROM 1, IC2, ROM 2, IC3, RAM 1, IC4, RAM 2. Now let us do that. Addressing please. A0 to A9 here. Don't care specified indicates I can place any address in that range of 1K. I repeat, don't care specifies I can place any address in that range. Any. Don't care. Any means it can be any. Don't care. It can be 0 or it can be 1. So, starting address all zeros, ending address all ones. So, in that case, let me go ahead to IC2 also same, right? Yeah. Ten address lines. So, IC3 11 address lines. One more is used. Hope you are clear with the frame. So these lines, what I mentioned, are address lines. ROM address, RAM address. Are you clear? So remaining are chip select lines. No, 11, 12 are chip select lines. So let me place that. So first line 0, 0. Second line 0, 1. Third line 1, 0 default. Fourth line 1, 1. First I am placing default chip selection. Let us see whether it will match or not. So I have just placed default chip selection. Let's see whether it will match or not. Anyhow, the last two are unused lines. 13, 14, 15. Yeah, all these three unused lines. 12, 11 only in the picture. Unused. Right. So, unused lines must be always what? Zeros. We should always keep them as zeros. So, we'll fill it later. Now, here one line is extra kept unused. See that? Here the place is vacant. Here also the place is vacant. So, we should fill that number in such a way to get the sequence of the addresses. Sequence of the addresses. That is very important to follow. We need these addresses. So, we should place this bit accordingly to make on. So, placing what, I will be getting that address. That is very important for us to know. Placing what, I will be getting that address. Yes, please. So, assume starting address I want 0000, ending address I want 03FF. That's what the issue, right? So anyhow, place these as zeros. Unused always zeros. Yeah. Placing all don't cares as 0 and we'll get the starting address. Placing all don't cares as 1 will get the ending address. Because don't care beginning possibility 0, ending possibility 1. Correct? Don't care beginning possibility 0, ending possibility 1. Keeping that, let us cross check. Yeah. Anyhow, this bit is also unused in the case of this, right? So unused, 10th line. For ROM, it is unused. Unused, or I can say not used. Unused bit. Just make an invitation. Yeah, since it is unused, I kept as 0. Now let us cross check whether I am getting that address or not. So to continue, to count the starting address, I should place all don't care zeros. To count the ending address, I should place all don't cares as ones. Can we do that? Yeah. Yes, please. If I keep all don't care zeros, what is my address? 0, 0, 0, 0, 2, 0, 1, 1 is 3, F, F, 0, 3, F, F. That is my starting range. My ending range. So, I'm sorry. Yeah. Beginning, ending. If I calculate, beginning keep x equal to 0. So 0, 0, 0, 0. Ending keep x equal to 1. So 3ff. So whenever you calculate beginning address, keep don't care as 0. Calculating ending address, keep don't care as 1. That is a formality anyhow. So x calculation for beginning address, it is 0. For end address, it is 1. Please always remember this. Whenever you are calculating beginning address x equal to 0, ending address x equal to 1. So when I am keeping x equal to 0, my requirement is satisfied. 0, 0, 0. So when I am keeping x equal to 1, there also my requirement is satisfied. 0, 0, 1, 1, 3. So 1, 1, 1, 1, F, 1, 1, 1, 1, F. So first I see successfully completed. First I see calculation successfully completed. So place x equal to 0, I will be getting 0, 0, 0, 0. Place x equal to all ones, then I'll be getting 0, 3, FF. Are you clear? Yes. Second I see in case. Keep x equal to 0, again for the beginning address. But this is 1 here. So 1 triple 0 is 8 now. 1 triple 0 is 8. But what is my second address range? See here 0, 4. 0, 3 continuous. 0, 4. 0, 7 continuous. 0, 8. Like that. I hope you need to just notate, make a notation to that. 0, 3 continuation, 0, 4. 0, 7 continuation, 0, 8. 0, triple F continuation, 1, triple 0. Sequence, address is always in sequence. In sequence. Right? It is supposed to be. Right? Then come to speak about this. To maintain that, now I have to change this. If I am keeping 0, 1 here, so what is happening? So it is becoming 8, 1 triple 0. I don't want to begin with 8. I want to begin with 0, 4. Hence, let me change this. Yes, please. How should I change? Continues this 0 and keep unused bit as 1. Then I got 4, you see. 0, 1. So 1 double 0, 4. If I place x equal to 0 starting address, no. So 1 double 0, 0, 0. So to get that starting address, I have forcefully maintained unused bit as 1. Please remember that. So I have forcefully maintained unused bit as 1. Then only I got the beginning addresses, this one. Yeah. Now continue. Beginning, ending. Beginning, ending. How will I give? Beginning is 0, 0, 4, 0, 0. 0, 4, 0, 0 to 0. All ones you keep. 1 triple, 1 double 1, 7. F, F. If I just keep all ones, 1, 1, 1, 7, F, F. So 0, 7, F, F. I think I'm clear. Okay. So beginning address, ending address. Zero 4 0 0 to 0 7 triple F. So what is this? Unused. Unused kept as 0 1 XX, right? Yes, please. So now keeping unused bit to 1, I got that address. So 0 4 0 0 0 7 FF. Now let me continue that for next one. Yes, please. For IC3, yeah. IC3, what is starting range? 0 8 0 0 to 0 triple F. 1 triple 0, 1 7 FF. To get 0 8, now I have to change again this status here. To get 0 8, what should be my starting address? This should be 0, this should be 1. So, what is beginning then? 1 triple 0, 8 0 0. Beginning address, ending address. Yes, please. Beginning, ending. What should I say? 0 1 triple 0 is 8. 0 8 0 0. So 1 1 1 1 is F, no? So 0 F F F. It is 2K, right? Starting any address. So I see 2 is satisfied. I see 3 also satisfied. Now I see 4 is left. So I want 1 triple 0 starting. 1 triple 0. So here. Remove this. Keep 0. Yes, please. Now what is beginning? 1. This is 1 triple 0 0 0 0. So beginning address, ending address. Zero 1 triple 0, no? 1 triple 0 to 17FF. So 0, 1, 0, 0, 0, 1, 0, 0 to 17FF, how it has come? Keeping all don't cares once, 7FF like that. So when I am calculating, please always remember in this table, when I am calculating beginning address, keep all don't cares 0. When I am calculating ending address, keep all don't cares 1, because don't care possibilities 0 or 1. Here are the adjustments you see. What did I? First select line 0, 0. Second select line also 0, 0. Third one is 0, 1. Fourth one is 1, 0. Actually, if I'm having 4 ICs, what are these select lines supposed to be? 0, 0, 0, 1, 1, 0, 1, 1. I repeat, if I have 4 ICs to select, what must be default selection status? 0, 0, 0, 1, 1, 0, 1, 1. But if I'm keeping 0, 0, 0, 1, 1, 0, 1, 1, I'm not getting the address in the sequence. Something else is coming. But I want the address in the sequence. To get the address in the sequence, I made adjustment. What adjustment I made? I have continued IC1, IC2 both with 0, 0 select line. And then this 10th unused line, I kept it 0 for the first IC, 1 for the second IC here. Try to make a note. Unused line 10th for ROM is maintained as 0 for the first IC, 1 for the second IC, like how I got the address sequence. Please remember. So how to calculate beginning address? Keeping all don't cares, zeros. How to calculate ending address? Keep all don't cares, ones. Anywhere, don't care possibility could be always 0 or 1. Now my first IC ranges for 00003FF and the binary number is given. Second 04007FF, binary number is given. So 08 to 0FFF, this is given. So 1000 to 17, this is also given. So the chip selection sequence must be according to the address selected. I repeat, chip selection sequence must be according to the address taken. Actually, default chip selection is 00011011, but I have not taken that. I did in this way: 00 constant, unused line 0 for the first IC, 1 for second IC. So 0, 1 and 10, like how I went on. So just check out, and this part play a key role in connecting the ICs. So what are the fundamentals taken here? Starting address not mentioned, hence start from 0000. Go by sequence, because go by sequence CPU is comfortable to work. If you give gaps in between the gaps, again to fill that, it is difficult to make some folds. Otherwise, CPU is always designed to communicate with line by line incrementing, one by one incrementing. Program counter, as you say, one name, which makes a count of the address calculations, is always default designed to get incremented by 1. Next line, next line, next line, like that. But if you miss some pages in between, miss some lines in between, so it will be difficult for CPU to communicate. This concept of address range is not in the sequence. How to communicate with? All those I'll teach you in the subject microprocessor. Anyhow, this is not the part of this subject. But here only one thing remember: if he did not mention any address range, specify always default range. Take always default range. Please remember that. Now here, this is my hexadecimal space map. This is my voltage level binary space map. Shall we continue? I selected these lines, bits of them, to get this address. Please remember, I'm just once again rehashing. I selected these bits to the requirement of me. If I go on default as 00011011, it doesn't matches to my requirement. So I made an adjustment. What is that adjustment? 00 constant for the first 2 ICs in select line. Because I have unused line here, because ROM requires only 0 to 9, 10th line unused in the case of ROM. So that line I have used it with 0 for the first IC, 1 for the second IC to get the sequence. I hope you're clear. Now let me continue to draw the diagram. Yes, please. 2K into 8 by 1K into 8 ROMs, or 4K into 8 by... Yeah, the same problem. Let's draw the diagram. Step number 4. Take only chip select table from that. Only chip selection table. Yes, please. So who are involved in chip selection? Address line 12, 11 and 10. 3 are involved and IC. Hope you remember. 12 and 11 00 with 10th 0 IC1, ROM 1. 12 and 11 00 with 10th line is 1, ROM 2. So 00 constant, 10 0 ROM 1, 10 1 ROM 2. So 0 1 of this is not bothered, RAM 1. 1 0 of this is not bothered, RAM 2. And I have just taken chip enable selection separately from this. Yes, please. Yeah, and I've just taken this part separately, chip enable part. Just let me identify. This part. This part is chip enable part. Chip selection, we've taken only 2 lines, but 10th also involved forcefully to get the address range. So that part I have copied. Yes, please. Now this is how my diagram is. Now let me get this. Yes, please. Let me draw the diagram. Now I want to draw the circuit. So how many memory ICs? 4 memory ICs, right? Yeah. What are these address lines? ROM 1, 1K into 8. ROM 2, 1K into 8. RAM 1, 2K into 8. RAM 2, 2K into 8. So 2 1K into 8 says 2K. 2K into 8 says 4K. Yes, please. Now address lines. Then extra address line only for RAMs. Notations. And this is A0 to A9. 10 lines common to all the ICs. And here a 10th line. 1 line extra only to RAMs. And that is how I did, right? So 0 to 9 and 10th line. Come back to speak. Now what I need to identify is 8-bit memory, no? So data lines 0 to 9, 0 to 7, I'm sorry. Bidirectional 0 to 7. Data notation D0 to D7, D0 to D7, D0 to D7, D0 to D7. Correct? So I have 2 condition here, no? Problem is a condition, you remember? Condition 1, ICs with only one chip select line. I'm assuming CS1. This is high enable. I repeat, ICs with only one chip select line, assume CS1, high enable. So, this is how my select line, CS1. What do that requires? Obviously, high signal, right? So, CS1, high enable. It need logic 1. So, 1 to enable that. Now, let me take a decoder, 2:4 decoder. Four outputs. E1, E2 bar, as we know, just like chip enable. 2 input. Here, D0, D1, D2, D3. 2:4 AH decoder I have taken. 12 and 11 I wish to connect to address lines here. Decoder input. If 12, 11 is 0, 0, this is enabled. 0, 1, this is enabled. 1, 0, this is enabled. 1 and 1, this is enabled. Correct? Now for the first two ICs, try to understand the logic here. 12, 11 both are 0, 0. 10th 0 first IC, 10th 1 second IC. That is how the logic for ROM1 and ROM2. I repeat, for the first two ICs, 12, 11 both are 0, 0. 10th 0 ROM1, 10th 1 ROM2 is what the logic here. So now I want to take AND gate. AND gate. So this D0 common to both of them. Connect D0 in common. Also do this. So this D0, 0, 0 goes to both of them. 10th line 0 this one, 10th line 1 this one, right? So inverter. And straight line. Over. So A10. Completed. So here if I get 0, 0 input, this both are activated. 10th line 0, this is enabled. 10th line 1, this is enabled. Over. So my ROM1, ROM2 selection is completed. Anyhow, VCC default for E1, ground default for E2 bar. Now, D2 is 0, 1 selection. That is for RAM1. Here, D1, D2, 0, 1, 1, 0. So, D1 goes to this. D1 goes to select this, D2 goes to select this, D3 unused. Over. So if my line is 0, 1, this is selected, 1, 0, this is selected, completed. My structure is done with a 2:4 decoder along with 2 AND gates and 1 inverter. So 4 ICs are connected in combination. 0 to 9, the 10 lines are common for all because all are 1K, 1K, but they are 2K. So one more line extra required, I have connected 10th line. And to enable 1 out of 4, I have taken decoder. I repeat, to enable 1 out of 4, I have taken decoder. But extra, not only these 2 lines of 12, 11, I do have a 10th line for the first 2 ICs in selecting. Hence, I have taken 2 AND gates to distinguish between by 10th line. 10th is 0, this is selected. 10th is 1, this is selected. So 12, 11 constantly 0. 10th is 0, this is selected. 10th is 1, this is selected. 12, 11 constantly 0. 10th is 0, this is selected. 10th 1, this is selected. And these two are anyhow independent, no? 0, 1, 1, 0. So this is how, if ICs are having only one chip enable line, the construction of the 4 ICs together by a decoder along with 2 AND gates and inverter can be designed. Now what hardware is used? 2:4 decoder plus 2 and plus 1 not. Now, in the very next case, let us see how to do this if ICs are having 2 chip enable lines. I repeat, if ICs are having 2 chip enable lines, how to construct the circuit, let's look into. Now, let's see the next part. If ICs are having 2 chip enable lines, how would we connect them? So, previously, only one select line CS1, but now the same problem, ICs with 2 chip enable lines. Let's see how do we connect. Oh, yes, please. Yeah, here the condition. ICs with 2 chip enable lines. CS1, CS2 bar. Yes, please. Yeah. Now let me draw the diagram. Here are my 4 ICs. Common address lines anyhow. A0 to A9. Extra address line A10. Data lines bidirectional because RAM. Yes, please. Notations A0 to A9, A10, D0 to D7, D0 to D7, ROM, right? D0 to D7, RAM, D0 to D7. I see ROM 1. What is the size? 1K into 8. ROM 2. What is the size? 1K into 8. RAM 1. The size is 2K into 8. RAM 2. 2K into 8. So totally 2 of 1K into 8. 2K. 2 of 2K into 8. 4K. And now let's see how do we enable this IC. ICs are having 2 enable lines. 2 chip enables. CS1, CS2 bar. CS1, CS2 bar. CS1, CS2 bar. CS1, CS2 bar. High enable, low enable, as we know. Notations. CS1, CS2 bar. CS1, CS2 bar. CS1, CS2 bar. CS1, CS2 bar. So, high enable, low enable, both. What are the requirement of the signals? 1, 0, 1, 0, 1, 0, 1, 0. When they get 1, 0, they will be enabled. I told you, enabling one of it, it is only partially ready. Disabling one of it, switched off. So, enabling only both, it will catch up to work out. So, every IC required 1, 0 in default to work out. Now, what does your chip selection table is mentioning? So, 121100 constant, 10th 0 first IC, 10th 1 second IC, 121101 for third IC, 121110 for fourth IC. That is how we have to work out. So, we have to connect 12 and 11 0 for both. So, why don't I connect OR gate here? Yes, please. Join these two. Take an OR gate, OR. Give the inputs 12, 11. A12, A11. Very good. So, 10th 0 to first one, 10th 1 to second one, right? Yeah, 12 and 11 both 0, 0. Our output is 0. So, this will enable both of them. Correct? Now, 10, 0 first IC, 10th 1 second IC, right? That is how the distinction here. 12 and 11 both constantly 0. 12th 0. So, 10th 0 first IC, 10th 1 second IC. So, let me connect inverter here. So, and let me connect here direct. Which line? A10th line. If A10 is 0, this will get 1. If A10 is 1, this will get 1. So, like how the lines are ready. So, 12, 11 constantly 0, these two are ready. And 10, 0 makes this activation, 10, 1 this makes it activation. See, 12 and 11 is partially getting ready. Only one enable activated by 0. So, second one activated by 10th line. So, next 0 1 for RAM 1, no, 12, 11. 12th 0, 11th 1. 12th 0. A12th 0, A11th 1. And this side, A12 1, A11 0. I have directly given. So, see the status of this. So, 0 1. Yeah, 0 1. 1 0. So, 1 0. So, directly that status is given to activate the IC. 12 and 11 is anyhow, 12 is 0, 11th is 1. And similarly, the status also 12, 1, 11, 0. So, one by one, all four are activated. So, what hardware is used? Guys, try to understand here. Only OR gate inverter. Only OR gate inverter. Nothing else. Nothing else. So, the hardware involved. Only OR gate plus inverter. Such a simple logic. Such a simple logic. Without decoder, without AND gates, nothing more involved. Can I make a note? Very important note. Extra chip select line. I repeat, extra chip select line may increase IC cost. But it helps reducing the design cost in assembling. Please tell me. Repeat once again. Extra chip select line may increase the cost of the IC, but it reduces the cost of assembling like this. Previously, ICs are having only one chip enable line. At that time, what happened is, so we have used 2:4 decoder, 2 AND gates, 1 inverter even. But whereas here, only one OR gate, one NOT gate has solved the purpose. Complete. So, this is how the memory ICs assembling will take place. So, how do you? First, you would be framing a basic requirements. How many address lines for RAM, how many address lines for ROM, and how many common lines, how many extra lines for other ICs, how many address lines to be taken as chip select lines. And always remember one thing, after completion of address lines to ICs, the most significant part must be taken for chip selection. Always most significant, constant remaining distinction. Like that we have to go, right? So our address constant MSB distinction. So MSB is always the distinction part to make up for a chip selection. So chip selection lines should always be placed in MSB part, most significant part. So A0 to A9 for ROMs, A0 to A10 for RAMs. Later 11th and 12th taken for chip selection. That's most important part. Then we went with, we just assemble them without second chip enable, only CS1. So hardware is 2 is to 4 decoder plus one UDs, two AND gates and one NOT gate. And we went with 2 enable lines. It has drastically reduced using only OR gate and inverter. In between, how did we frame? Step number 1 is basic requirements. Step number 2 is hexadecimal space map. Step number 3 is voltage level, binary level space map. That is important for us. But when you're framing a space map, the most important part is your requirement in the sequence. Address frame should be in the sequence, but not zigzag. If it is zigzag, what is the drawback? How we could do? All this I'll discuss in microprocessor, as I've already told you. Address framing must be in the sequence, either in the table or in the connections given. That is very important for you to remember. So to frame the address in the sequence, I made some adjustments. Otherwise, if I have 2 chip select lines, default selections could be 0, 0, 0, 1, 1, 0, 1, 1, right? But I have taken 0, 0 for both ICs, 10th line 0 for the first IC, 10th one for the second IC, which is unused. And come back to speak, 0, 1, 1, 0 I have given, last one 1, 0 left unused. And this is how memory ICs will be assembled. And we have 2 more models in this structure, and different ways to go and changing the data bits even. So here, D0 to D7, D0 to D7 data is common. It is as if 2K into 8 by 1K into 8, 4K into 8 by 2K into 8, like that. But in the next models, we will even see addressing different data capacity is also different. Like how we'll practice different exercises, since it plays a very, a key role for competitive requirements. I told you industrial requirements in all the cases. And let's see how best we do in the next model working on. Before we go with the model of advanced concept of assembling memory ICs, I just wish to cover a small topic left in the theoretical classification of memories in the previous class. Nothing but memories according to the position of data after storing, static and dynamic. A small concept is left. Let's see and complete. Yeah. Based on the position of data after storing, memories are classified as static and dynamic. The definition here is data is stable in which it is stored. Data is stable in which it is stored and involved stable storage elements, transistors. So, data is stable in which it is stored, involved stable storage elements, transistors. Nothing much in. Dynamic memory. Data moves from one cell to the other. That is what the concept of dynamic memory. Data moves from one cell to the other. Because charge coupled capacitors was used. charge coupled capacitors are used. Thank God. Capacitors in the structure of memory. How long the capacitor can hold the data? It can be as long as we want, right? So anyhow, it is not the real capacitors involved in dynamic memories. Let me show you the structure of that to understand what is dynamism and how the dynamic concept is achieved and why dynamism even. So I'm just giving you an 8-bit dynamic storage cell. 8-bit dynamic storage cell. I'm taking 8 capacitors here. So here. And these are 8 capacitors. So here a comment. Not original capacitance. Come on. It is tray capacitance. Produced by MOSFET. Tray capacitance produced by MOSFET. Coupled to the subsequent to create a dynamism. I repeat. Coupled to the subsequent to create dynamism. Let me tell you what exactly the story. Now, whether it is tray capacitance or original capacitance, the feature of a capacitance is drop as soon you charge it, right? Once you complete your charging, it gets discharged, drop will start. Now, every capacitor will be dropped, as I can show. Discharging will begin. Discharging will begin. Every capacitor drops down the charge. What will I do is, I'll connect this discharging energy of this capacitor to the subsequent. Connect the discharging energy of this to subsequent. Connect the discharging energy of this to subsequent. Couple the charge. Charge couple the capacitors. Charge couple the MOSFETs. So I can say here. Couple the charge. Use this to charge the next one. Use this to charge the next one. Use this to charge the next one. 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 Bring this to charge the first one. Now what happened? Charge coupled nature is happened. Now if I want my data to be like this, if my example of data is 1011 0110. So if I want that data from that, charge to high, low, high, low, sorry, high, low, high, high, low. Now what happens? Once if I leave it, it will be moving, right? It will be circulating. So what happens? The shift occurs. So here one transfers here. After one cycle, what happens? Show the movement. 1 here, 0 here, 1 here, 1 here, 0 here, 1 here, 1 here. This 0 will come here. So what happened this? And I got 5B 1011. What is initially stored? B6. So B6 stored, after one cycle, it has happened to be 5B. So the movement of data, circulation. So not original capacitance, it is a stray capacitance produced by MOSFET coupled to the subsequent to create dynamism. So what is dynamism? The energy of one capacitor moving to the subsequent is dynamism. So how dynamism is created? Coupling the charge between them, MOSFETs, the stray capacitance coupled between them, moving to the next happen to create the dynamism. And why dynamism? Please tell me that. Yes, please. To create circulating resistors. What is that? To create circulating resistors and delay lines. So application of dynamic memory says that to create circulating resistors and delay lines. One drawback these dynamic memories are having, negative, is that constant refreshment required. Constant refreshment to required to fill the energy loss. In dynamism. Because even after you couple them to transfer this charge to next one, this charge to next one, this charge to next one, but complete energy will not be transferred, right? Some loss will be there in the transformation. To fill that loss, we need a constant refreshment. Like how? Static memories are designed with the stable storage elements transistors. Dynamic memories are created by using a dynamic storage elements, charge coupled capacitors, MOSFETs, whose stray capacitance coupled each other, or where the energy transformation will occur like that. So the data circulation is created. Delay lines can be structured in the industrial applications in the real-time process. And this is how the classification of memories, a theoretical topic, plays a vital role to get 1 mark questions in the competitive exams, interview questions. A lot I have posted, right? ROM is a RAM, how is it true? And then I posed it how a primary memory made up of semiconductor elements is permanent in the nature of storage in the case of ROM, read-only memory. And like how a lot of questions I raised in interview perspective from the topic types and classifications of memories. Whereas in the problems part, assembling memory ICs do play a vital role with a gate and engineering services to get you always, every year the best question will be framed from the assembling memory ICs. So the next models of assembling memory ICs we'll see at the immediate session. Thank you.